In this example, we're given the set B consisting of these three polynomials here, 1 plus t, 2t minus t squared, and 5 plus t squared. And we are asked if this set B is a basis for P2. Now, in the previous example, we were given some vectors in R3, and in that case, all we really had to do was use the invertible matrix theorem, take those vectors, put them into a matrix, and row reduce the matrix. If it's row equivalent to the identity, then yes, the set containing those vectors is a basis. And if it's not, then no, the set isn't, because all of those statements in the invertible matrix theorem are if and only if statements. Here, though, it's not so straightforward. So what we're going to do is rely on the isomorphism from P2 to R3. So to review real quick, here's a picture of that isomorphism. So here I've got the set P2, here is the set R3, and the isomorphism is what I've called M here. And it's a mapping. And it'll take, say, this vector P in P2 and map it over to this vector P with the brackets around it and the D, which stands for the coordinate vector of P relative to the basis D. Over here is my basis D that is in P2. This is what we call the standard basis for P2. It contains the vectors 1, t, and t squared. And we'll see why that's the standard basis in a little bit here. And the definition of an isomorphism is down here. It's a one-to-one onto linear mapping. So there's really three things that characterize this mapping. It's one-to-one and onto, and it's linear. One-to-one and onto together mean that it's invertible. And I've got arrows, if you notice, on both sides of this line here, connecting P2 and R3. That means that the mapping goes in both directions. Okay, so how are we going to take advantage of this isomorphism? Well, the first thing we need to do is write down this set D. So we'll do that 1 t squared. And this is the standard basis for P2. And the reason is, the reason we call it the standard basis is that we can observe the coordinate vectors for any vector in P2 relative to this standard basis. So for example, if we say, let's take something simple like 1 plus t, this first vector in B. If I want to write down the coordinate vector of that polynomial, which remember is a vector in this vector space P2, relative to the basis D, well, let's say that's C1, C2, C3. So it's going to be a vector in R3 whose components are C1, C2, C3, and I need to figure out what those are. Well, the definition of them is that 1 plus t is equal to C1 times 1 plus C2 times t plus C3 times t squared. Notice that 1, t, and t squared are the three vectors in D. So we could call those, say, D1, D2, D3 if we wanted. But I just left them as 1t and t squared. Well, from this equation it's pretty easy just to observe that C1 is equal to 1. C2 is also equal to 1. And C3 is going to be 0. That's t squared there. All right, so we can say the coordinate vector of 1 plus t relative to D is the vector 1, 1, 0. And let's do another one. Let's do the next one, 2t minus t squared. And you'll see how easy it is to just observe this. So I'm going to think of this vector 2t minus t squared as something times 1 plus something else times t plus something else times t squared. Well, there's no constant term in here, so the first component is going to be 0. So 0 times 1 plus 2 times t plus negative 1. So this minus is really a negative 1, so we consider that a 2, and then this is a minus 1. So the next two components are 2 minus 1. And then we can get the last b, 5 plus t squared. Its coordinate vector is going to be 5 times 1 plus 0 times t plus 1 times t squared. Okay, so the great thing about the isomorphism is anything that happens in, let's go back over here, anything that happens in R3 with vectors also happens in P2. And in particular, we say that linear dependence relationships are preserved across the isomorphism, which is just a fancy way of saying if a set of vectors is linearly dependent in, say, P2, the corresponding set of coordinate vectors is also linearly dependent in R3. And any linear combination of vectors in P2 will have the same linear combination for its coordinate vectors in R3. So instead of working with these three vectors in the set B, I can work with their coordinate vectors that we found here, and here, and here, in R3. And if those three vectors form a basis for R3, then the polynomials up here in B, or more specifically B itself, forms a basis for P2. So let's try that. Let's see if we can do that. Well, this just simplifies to the first example we did. So let's say A is the matrix 1, 1, 0, 0, 2, negative 1, 5, 0, 1. Row reduce it. I'll skip that part. You can do that on your calculator. You'll find that it row reduces to the 3 by 3 identity. So the columns of A form a basis for R3. And here's the punchline. And by the isomorphism, from R3 to P2, you could also say from P2 to R3, because remember, it goes in both directions. B is a basis for P2.